Hello everybody and welcome to the latest edition of Conceptual Astrophysics videos, a series in which we show how to set up and solve introductory astronomy problems. I'm your host, Dr. Christopher Sorolla. Today we're taking a look at Kepler's third law, but with a twist. Instead of talking about, say, the orbital characteristics of a planet or an asteroid about the sun, I want to use the generalized version of this idea to find the mass of an object. So this is an interesting question. How, for example, do we know the mass of the Earth? The Earth is very big. You can't put it on a scale, for example, right? So how do we know that idea? Well, it turns out we can calculate that by looking at other things, specifically what the Earth's gravity does to objects in orbit about it. And we're going to use the moon for that purpose. So the formula for the generalized version of Kepler's third law of planetary motion looks like this. So you might remember in a previous video we derived this. If you didn't watch that video, you can either go back and look at it later or just simply accept the result for us here. But this particular formula, this is a general version of Kepler's third law, says the square of the period is equal to these numbers multiplied by the cube of the distance between the objects. Now, what are these numbers? 4 and pi squared. That's our pi number there. Nothing different there. Capital G is something called the universal gravitational constant, and that number is well known from laboratory experiments. That's right here. Capital M is the mass of the object. Specifically, and we have to be careful about how we say this, capital M represents the mass of the object that is being orbited, not the object in orbit. So we gotta make sure we get this order of ideas correct. So what we're really doing here is saying, look, there's an object that orbits, say, the Earth, like a satellite or the moon. It has orbital characteristics, such as the amount of time it takes to orbit, the orbital period. It has the semi-major axis, or average distance from the Earth, right? Take those two numbers, the orbital characteristics of this, you can use that to find the mass, not of the object, but of the Earth. And what this is basically doing is it says, oh, the Earth has gravity, has an effect upon objects around it. Let's measure the effect of the Earth's gravity on objects around it to calculate the mass of the Earth. And you can do this, by the way, for any object. We could do this for Jupiter, we do this for the sun, we can do this for all sorts of objects. Now, one more thing I want to do or want to talk about here as we go along. To do this properly, we do have to be consistent with our use of units, how we express our numbers. And so you'll commonly find, if you look up, say, the distance from the moon to the Earth, that would be this number. And orbital period of the moon is often cited as this number, okay? We really can't use those numbers, or at least we have to be careful about the use of those numbers, because we don't want to mix up our unit usage. So we need to make sure everything's consistent. So in places like this, it's common to use what are called standard units, or basically the metric system, which means distances are expressed in terms of meters and time is expressed in terms of seconds. So we need to convert this number into meters, this number into seconds. So before we go calculate anything or manipulating that equation, let's do that. So R is 384,000 kilometers. This conversion is kind of easy. For every kilometer, there are 1,000 meters, right? Kilo is the prefix that means 1,000, right? So we simply multiply that number by 1,000, and we'll get this as a result. Now, I'm going to express it like this, rather than put it out in full. Use scientific notation for that. Notice that I've got it set up on purpose. Kilometers cancels kilometers. Okay. So there's my distance in meters, right? How about the period? Period's a little trickier, but not too much trickier. So 27.32 days. Now, by the way, this is not the period that you would notice by the phases of the moon. That period is called the synodic period. That period talks about how the moon orbits the Earth and shows its different phases to us. But because that involves light from the sun, that also invokes the orbit of the Earth about the sun at the same time. And so that is what you normally call a month, if you will. And that lasts about 29 and a half days. That's not what we're using here. We're not concerned about the sun's influence upon what we see. What we're interested in here is how long it takes for the moon to actually make one orbit about the Earth, forgetting that the sun's there, it doesn't matter. So that's why this number is a little different. That's why when you look up in a table, you'll see things like this. This is what we call the sidereal month, or the sidereal period of the moon's orbit. So just to mention where this number comes from. Now, to convert this, I already have a conversion written up here. It's 86,400 seconds in every day. Now, by the way, if you think about it, you can come up with that number yourself, right? And if I do that particular calculation, I get a little over 2 million seconds. It looks like that. Again, notice my conversions here. I've arranged it so that days cancel days here, and I'm left with seconds. All right. Now I have my numbers, my inputs. I can go ahead and get started. One more comment about that, real quick. When we look at capital G, the universal gravity constant, it's nm squared over kg squared. What's all this? M squared, that's meters. So that's okay. We've got meters involved here. Kg stands for kilograms. That's the standard unit of mass in the metric system. So ultimately, when we calculate the mass of the Earth with this idea, we're going to come up with kilograms as units. This capital N as a unit is something called a Newton. Newton is a meter times a kilogram squared divided by second squared. Kind of messy, I know, but that's what it is. That's an abbreviation that's used quite often in physics, but it is still standard units. It's still invoking meters and seconds and kilograms, and therefore everything will work out correctly. If we don't use this, we will get an answer, but it won't be in the proper units. We won't have a sensible answer. So again, we're being consistent with units here. Okay, so let's take this equation and take a look at it. Now, you rewrite the equation here quickly and ask, how do we then calculate for the mass? Well, it's simplest to solve the equation for mass. How do we do that? Well, we're going to pull a trick that's similar to other tricks we might have used in the past with algebra. Let's multiply the entire equation, which means both sides, in such a way as to get mass isolated by itself. Now, how can we do that? Well, mass is being divided by over here. We don't want to be divided by mass. We want mass to be on top, so to speak, right, by itself. So let's multiply both sides by mass. By the same token, we're going to move mass over to the left. Let's get this t squared to the right. Let's divide both sides of the equation by t squared. Okay. When I do that, m on the right divided by m cancels. M on the left is all by itself. Now the 4, the pi squared, and the g are still here. That's fine. The r cubed is left alone. We haven't touched that. And then the t squared, if I divide the left-hand side by t squared cancels t squared, and that disappears. But I have to do that on the right-hand side as well. Divide by t squared, that ends up here, like this. So this is the algebra solution for the mass. All right. Now we can plug in numbers. So let's do that. So 4 pi squared. Now g is 6.67 times 10 to the minus 11th in these interesting units that we talked about, like that. So I've got that so far. R is 3.84 times 10 to the 8th power meters. Notice that that number is cubed, because this is cubed, okay? That means both the number and the unit are cubed, right? For t, that was 2.36 times 10 to the 6th seconds, and that whole quantity is squared. Again, both the number and the seconds get squared there. So, as far as your calculator is concerned, this is where you should probably turn to your calculator if you're following along. Why don't you go ahead and you can either pause the video, for example, or play with the numbers in your calculator while I'm talking. The units aren't taken care of by the calculator. Calculators don't know anything about units. That's our job. But we can do that. And as I said before, we've already set it up so that we'll come up with kilograms. Now, if you're not convinced of that, you can do what I suggested before. Take these newtons. Newtons are really, or I'll write off to the side so people can see, a newton is really a kilogram multiplied by meters squared and divided by a second squared. So if you were to take this and substitute it in there and then very carefully manipulate the units, you will find that we'll come up with kilograms in the end. That's a side job. I'll let you do that on your own if you wish to do that, to convince yourself that it works. Okay, but the rest of this, multiply through, and lo and behold, the value we get is 6 times 10 to the 24th power kilograms, which is, rounded off, the mass of the Earth that you all see in your textbooks and your papers and such. So that's how we measure the mass of a planet or a star or even a moon. When objects are so huge, and this is a problem that really is kind of restricted to astronomy, right? For the most part, this isn't a thing that's a biology or a chemistry issue. This is kind of an astronomy issue. But how do we measure the mass of an extremely huge object? Well, we don't measure it directly by putting it on a scale. Instead, we measure the effect of its gravity upon other objects around it. And so, if I have a small object, like the moon, and as big as the moon is, it's still less, it's just about 1% worth of what the Earth is. That's very small. We use the effect of the Earth's gravity on the moon to tell us how much mass the Earth must have to make that effect happen, right? That's the logic. So, one more thing I'll say, if you look in a typical, say, textbook or online, the number that's quoted will be a little bit more precise. It's usually something like 5.98 or 5.976 or whatever instead of 6.0. A couple things. First, I've rounded off here. Second, the moon does have a small amount of mass, but it's not zero. And what we've really calculated here, to be quite honest, turns out to be the mass of the moon plus the Earth together. If I want to be a little more careful about how I say that. If we do this on a much more careful basis, we would find out that the Earth's mass is a tiny bit less than that. Not by much, but a tiny bit less. For our purposes, this is perfectly fine for what we've done here today. Okay. But anyway, so there are details that we could follow up on is what I'm saying, but they are details. This result is good to how I've expressed it. 6 times 10 to the 24th power kilograms, mass of Earth. And this, folks, is how you mass or weigh a planet. Hello, everybody. Thank you for your attention. I am Dr. Christopher Cirola for Conceptual Astrophysics, and clear skies, everybody.